My name is Clement. I am a medical statistician at the Nuffield Department of Medicine at Oxford University. And prior to that, I was a clinical trial statistician at Imperial College. And then I had my PhD and my postdoc at Cardiff School of Mathematics and the Oxford Statistics Department, respectively. So today we are going to talk about the introductory statistics session 2. So we've already done the session 1. So if you've not watched that, the videos are out there, and then I think you should watch that before you attend to this. So just to recap some of the outlines. And so basically, again, we'll just touch a bit on the upcoming or the ongoing stats teachings and also future plans. And then today we are going to introduce very interesting statistical applications. One that probably are some of which are less used most of the times in most health studies. However, if you look at the nature of the data that are collected, these kind of models kind of suit those studies in the best possible way. And so today we are just going to learn about the awareness of such models, and I'll try as much as possible to be less technical, and there'll be quite a couple of examples so we could appreciate these methods. So today we are going to touch about hierarchical regression and then how people confuse that for multi-level regression. So we'll touch a bit on that. And then we touch a bit on structural equation modeling. Maybe you've heard of it, you're not too sure what it entails, or probably you've heard of it, but depending on your study, you never thought it could suit into that. So today we are going to learn and see if indeed you could also adopt that for your studies. So as I said the last time, using the right tool for the right job is always imperative. And depending on your research questions and its complexity, sometimes you might want to use some of these advanced methods. And then we are going to touch a bit on time to event analysis, properly known as survival analysis. And in this case, we're going to look at the case of stratified versus unstratified, and then think and learn about an extension of the standard survival models, which we call the multi-state Markov model. Because of time, I couldn't touch on one other advanced method, which was very keen for me, and that is called functional data analysis. I'll just do the concluding remarks on that. Okay, so once again, last week we did the introductory stats 1, which is basically talking about a brief overview about some of the most important and basics and terminologies and things you need to know about statistics, and the fact that your data, the type of variables could have impact on the kind of analysis you do, and can even inform your choice of statistical methods and so on and so forth. And then we did that in the case of parametric, non-parametric, multivariate versus univariate, and so on and so forth. So if you've not watched the first video, I think you would want to watch that. So today we are going to introduce the start session 2 and repeat it on Friday as well. And once again, for future sessions, we are planning of hosting or having this kind of interactive session where a researcher or group of researchers will present the statistics bit of their works, get feedbacks from not just me, but also within a team in the case of brainstorming, and then for others to also learn about other methods that people are using out there across different disciplines and different subject areas. So this is something which is still on the developing stage, and then so we'll still need your feedback to know the best way we should approach it. And we're also thinking about some drop-in sessions as well, and which is still in the developing stage. So your feedbacks are really, really needed. Constant hazard assumption. So to make life easier, we are going to use a data, like a well-known data, to explain some of these things and look at, if you are doing survival analysis, what are some of the most important things we need to achieve or we need to also report on. So we are just going to use a data which was obtained from some veterans administration. And so basically it was a lung cancer data. And it was obtained from a clinical trials where patients were randomized to either receive a standard chemotherapy or some experimental chemotherapy. And then the baseline, the primary endpoint or the main endpoint was time until death. And so we will talk about, so those, so here we are, so that is basically the summary of the data. So we just talk about some of the covariates or some of the predictors or the variables that they collected in the data. So we have, you see something called the Kano variable, which is just talking about the Kanofsky score, which quantifies patient overall baseline status. So, and then if the score is greater than 70, it implies that the patient is able to take care of themselves. If a score is between 40 to 60, it means that the patient requires some assistance. And if it is between, and often the minimum is 10, and then it's often recorded at discrete, in a discrete fashion. And so that's why it has been discretized in that manner. Yeah, and then we have a variable called die time. So this is just the time demand from diagnosis to randomization. And then we have age of the veterans. And then we have a variable called PROW. This is just an indicator as to whether the patient receive a PROW therapy before the study or not. And then we have a variable called cell type, which is the type of tumor. So we have 4 levels of that. So this is just to say that anytime you are doing survival analysis, the first thing is to produce some Kaplan-Meier curves. So these curves are what we call the survival curves or the Kaplan-Meier curves. And you can only do a Kaplan-Meier or produce a Kaplan-Meier curve for one predictor at a time. You cannot have like you cannot have it like an interaction, because keep in mind it's a univariate method. Okay, so you can only look at one predictor at a time. And but there's a take-home message. I think a disclaimer is that because Kaplan-Meier only focus on one predictor or one covariate at a time, people assume that the cost proportional regression, if you have only one independent variable in the cost proportional regression, that is a univariate cost proportional regression, or that's a univariate, or it's also a univariate method, which is true. But they also assume that if you now have set of predictors in your cost proportional model, then we now have a multivariate survival analysis. So, and I beg to differ, because as we said, multivariate has to do with, based on our previous session, has to do with multiple outcome variables. So suppose you were modeling the time to experiencing a certain event and the time to experiencing another event jointly, then I can now say that that is a multivariate survival analysis. Always remember that multivariate methods has got to do with multiple outcome variables. But if you believe that having one predictor in the cost proportional model is an invariant method, which is true, but having multiple predictors in the model, classify that to be multivariate. I beg to define, I want to call it a multivariable survival analysis instead. So by the end of this class, I don't want us to classify a cost proportional regression with several predictors as a multivariate survival model, because it is not. If it was jointly modeling time to experiencing or modeling two or more time to event data or outcome variable, then in that case we can talk about multivariate in that case. But if you have multiple or several predictors, we should rather call it, maybe, if you don't want to call it a multiple cost proportional model, because we have multiple linear regression, we said it has several predictors. Maybe we want to call it a multivariable survival analysis. Yeah. Anyway, so anytime you produce your Kaplan-Meier curves, we now ascertain whether there's significant difference in the survival probability or the survival curves between the levels of the outcome, the levels of the predictors you are exploring. And then the popular test we do is called the log rank test. We have different tests, but the log rank test is a popular test. It's similar to a chi-square test. So basically, once the p-value is not significant, then it means that there's no significant difference. And often, if there's an intersection, once the curves intersect at any point in time, then there's a guarantee, especially when it has two levels and there's an intersection, then there's an assurance that there's not going to be any significant difference. We can, if there are two levels, the only instance the test is going to conclude on significant difference is when there is no intersection. But we could have, let's say, four levels. Some could have intersection, but if you think about it, if you look at these two curves, though they intersect, if you are looked at those two alone, then there will be no difference between their survival curves, right? But if you look at these ones, that is specifically the small cells and then the adenal cells. If you compare that to any of the red and if you compare to the squamous or the large ones, there will be a difference there. So I'm just trying to give that disclaimer that if it's just two levels and there's any form of intersection, the test will conclude no difference. But when we have multiple or several, so for instance, if you look at the chemo or the Kanofsky status, the red and the green here, that is hospitalized status and the medical care status. They intersect somehow. However, there's no, the intersection is not, they intersect somehow, but there's no intersection between the red curve and that of the blue. So there's no intersection between the status of that self-reliant status and then the hospitalized status. So if in that case, there's a chance of significant difference. Yeah. So it's just like when you were doing ANOVA, we said that ANOVA will only conclude on significant difference if at least there's a pairwise difference between any pair of your levels. So if you have 3 or more levels, and then at least any pair is significant, then the overall test will conclude on significant difference. So it's similar to that. Okay, so this is just a summary. So it means that you can have these kind of nice graphs after fitting your cost proportional model. You could have these graphs are called forest graphs, and they are ways of trying to summarize your effect sizes or your hazard ratios and so on and so forth. And it even tells you, and these were produced in R. All the output you are seeing here, I already have written a code for that. So in case people are interested in just getting the codes so that they could replicate it for their study, I'm also happy to share that. So now let's think about after. So it means that you do the Kaplan-Meier curve to investigate or explore how the survival curves varies between levels of some predictors. And then you can now fit a cost proportional hazard if you are now trying to control for other potential other predictors and so on, and adjust for the effect of others as well. But after doing that, you have to, and you opt to test for the parametric assumptions. But so there are many assumptions, but the most important assumption that you really need to satisfy is the proportional hazard assumption. In R, we have some specific tests you can do. We have some proportional hazard tests, but there's a nice graphical thing you can do that is using the Schoenfeld test. So once the Schoenfeld test is significant, then it means that, and the Schoenfeld test is just a plot. So there are different residuals. There are different residuals in terms of when you talk about survival analysis. We have the Schoenfeld residual. We even have Martingale residual. We have different ones. But once you plot the Schoenfeld residual over time, okay, and then so this is the kind of graph you see. But of course, I told you that we cannot always make inference just based on descriptive summaries. Though the descriptive summary looks nice, but it is always imperative to do an official test. So there's a global p-value from the Schoenfeld test, and the global p-value tells if once there's significant, the p-value is significant, it tells that proportional hazard assumption was not met. And if it was not met, it could be due to not all the predictors. It could be due to at least one of them. So here we can also assess individually which ones met that constant proportional hazard proportional hazard assumption. So for instance, if we look at treatment, so this is the variable on treatment. So we could see that that assumption was met. So meaning that the hazard was constant across the two levels of treatment that we had in the study. And then, but if you look at specifically the cell type, the p-value was significant. And then if you look at the Kano variable, the p-value was significant. The others, it was not significant. So it meant that those that were not significant achieved that constant hazard assumption, but those that were significant resulted in why the assumption was not met. So once the assumption is not met, then it brings us to stratification. So the essence of stratifying a cost proportional hazard is that those variables that did not achieve that particular assumption, you could now fit the model and stratify with respect to that. By stratifying with respect to that, what it means is that we are we'll talk about after the stratification, the kind of outcome or output you see, and then what we mean by that. So just the take-home message here is that we only stratify with respect to a certain variable if that variable did not help us to achieve the constant hazard proportional hazard assumption. And then, as I said, there are other parametric assumptions. Since cost proportional is a semi-parametric, so we need to investigate all these. So don't just fit the model, get your forest diagram, and then just conclude that you've identified some predictors that predicted the survival times and so on and so forth. But you should also ascertain it's a parametric, it's a semi-parametric, so you should ascertain whether those assumptions were met, especially this particular one, which you can get nice graph like this in R, for instance. And then, so another assumption is that we should also examine whether there were outliers or influential observations. And then, so I've just summarized that there's a particular plot you could do. So another type of residual, as I said, we have the Schoenfeld residual, we have Martindale residual. We also have a deviance residual. So once you plot the deviance residual across the observation, we want to it's supposed to be symmetric, symmetric about with a mean of 0, or symmetric about 0 with a standard deviation of 1. And so, but if you look at this plot, as you can see, by symmetric, if you look at the normal curve, okay, I mean, it's just an example of what we mean by symmetric about 0. But if you look at it in this form, we expect that on the red line, we expect that the degree of the dispersion should be similar above and below that. But again, we are not seeing that. So here, keep in mind positive values. Those individuals, those points, each point represents an individual in the data. So those that are above the red line, it implies they died too soon. And so it means that is compared to the expected survival time. So these are individuals who died too soon. And those below the red actually lived too long. And then, so for very large and very small outliers. In statistics, you see a data or a value is an outlier if it doesn't fall within 3 standard deviations of the mean. Okay, so if here the mean is 0, and then if you look at 3 standard deviations of the mean, means that it shouldn't be above 3 or below -3. So if you think about it, in this case, we can't conclude that there are enough of evidence of influential or outliers, because if you see they are all within that 3 standard deviations of the mean, which in this case is basically 0. But here it's also, you could also have like a nice graph, just or a nice linear model, just trying to tell the kind of relationship between the residuals and then and then the observations. And then the next or the last assumption, which is most important, is that the cost proportional model is a linear model, right? It's looking at the linear effect of the predictors on the log odds or the log hazard. Okay, so but again, if they are continuous covariate, if you remember last week, we said that there are instances where some of the continuous covariates could have nonlinear relationship with your outcome variable, even for cases where the outcome variable is time independent. Okay, and we said even with that, we have to now fit splines or maybe transform the data and see if upon transforming, we can have something fairly linear. But with the help of additive models, we are able to now fit splines to such variables with nonlinear effect on the outcome and smoothing out those nonlinearity. And that is what we mean by additive models. One could even employ that methodology into this case. But here we are just trying to demonstrate how you'll be able to identify whether there's nonlinear relationship between your continuous outcome. For this assumption, it's not applicable to the categorical outcomes. So it means and to do that, we plot them. So I told you we've heard of 3 types of residuals. There are many residuals in survival analysis. We've heard of three types. We've heard of the Schoenfeld one, which is often used to test for the constant proportional hazard assumption. And then we've also looked at the deviance residual, which also help us to ascertain if there are potential outliers or not. And then now we are hearing another one called the martingale residual. So plotting the martingale residuals over time, what that does is that it helps us, once you see any pattern, if you don't see anything linear, or if you don't see any linear pattern, but you see any nonlinear pattern, then it tells that there's a nonlinear relationship between that particular continuous covariate on the outcome. So our entreat is that whenever we are doing survival analysis, we should investigate all these things because it can help inform another set of models we can use. So here I wouldn't go much into the detail because I've already talked about that. So I said that once there are time varying covariates in your model, so if you have a certain outcome variable that changes over time. So just imagine, let's say you are in parasitological studies where you were trying to look at how some set of predictors maybe influence some outcome. And then one of your predictor is number of parasites over time. Imagine, and we know that the number of parasites over time, of course, will change. Or let's say age. And then age could be constant when we are dealing with in the case of a cross-sectional data. But if we are doing the study in a longitudinal fashion, then it means the individual's age is also going to change over time. And that what that implies is that age now becomes time-varying covariate in that instance. So, and when you have such instances, we have another class of models called the Allen additive regression model, which is also a survival kind of, it's a form of Cox proportional model. But what it does is that it's able to deal with the time varying covariate. But keep in mind, although it can deal with the time varying covariate, it might not be able to deal with it might deal with the effect of the time varying covariate in the model, but it might not be able to deal with the constant hazard assumption. And of course, in real life, we are not always going to see the constant hazard. Most of the time, it doesn't even hold. And when it doesn't hold, you now need to think about other things to do. So always don't forget to test those parametric assumptions. And once they hold, then you are good to go. If they don't, we can now improve upon our model. So what stratification does is that, so if we have a certain variable, as we saw in the Schoenfeld diagram, for instance, cell type was significant, meaning that it didn't achieve the constant, or let's say the hazard were not constant across the levels of that particular variable. When it happens that way, what we do is that we now stratify the model based on that. By stratification, you can think about it like splitting the model with respect to that. So if the levels were 4, you are literally going to have like 4 class of models where we combine the results to make inference. Yeah, so that's basically what the stratification does. So it means if you stratify with respect to a certain variable, you will not get hazard ratios for that variable. It means that variable is just like doing mixed effect modeling, where you have repetition in time or temporal pseudo replication or spatial pseudo replication or repetition in space. And so, or you have some kind of nested data where you are trying to account for that nesting levels, but you're not interested in them. So you added them in the model as random effect. And then those predictors of interest were your fixed effect in those instances. So you realize that the effect sizes would only go in for those predictors of interest, but those that you added as random effect, you will not see any effect size attached to those variables, isn't it? Yeah, so you think about the stratification like that. It means that once you stratify with respect to a certain structure or with respect to a certain structure that was not helping to achieve that constant proportional assumption, by stratifying with respect to that, it's more like trying to split your data, split your model or construct your model to have different base rates or different hazard rates across the levels of that particular stratum. But when you achieve that, when you do that, it means you can't make any inference about that particular stratum or that particular variable that didn't achieve that constant here, because so that is something you need to do or you need to know. So in R, we can use this Cox pH function if we had removed this structure, that would have been the classical cost proportional regression. But in R, once you now bring a structure, this function called structure, around any predictor that you found from the previous assumption that did not achieve the constant proportional assumption, a hazard assumption. Once you put structure around that, it now you now have what you call a stratified. So in that case, that model you fitted is a stratified cost proportional model. And yeah, so that is just the simple thing you need to know. So once you summarize the model, you realize that if you were even looking at the Kaplan-Meier output, you realize that you now have different Kaplan-Meier output for each of the levels of the variable that you stratified with respect to. So that is something you have to note in this case. So here, it means that here I'm just considering all the predictors are in the model, but we now have cell type to be a stratum that because we are assuming that once you see a variable being considered as a stratum in your model, it means that it didn't achieve the constant hazard assumption. Yeah, and that's why. So that is just the take-home message. But another thing is that we have other class of survival models apart from the fact that the Allen's additive model can deal with the effect of some of these time varying covariate. We also have something called survival trees. I beg to differ, though we can call it random forest, but random forest is a class of machine learning. It's a machine learning technique that incorporates something called decision trees as well. But here we are just calling it random. We are also borrowing that name, random forest. So that this random forest I'm mentioning is not the classical random forest in the case of a machine learning, like classification tree, random forest or gradient boosting machines. That's not what I'm talking about. But here we are just, the easiest thing you can say is survival trees. So it means you can also have this class of models are nonlinear models. So it means that situations where some of your predictors have nonlinear relationship with your outcome, then one of the most robust ways to model such is also trying to use what we call those survival tree models. And with that, it's a nonlinear model and can also deal with overfitting because you can prune the tree and in the best possible way to now minimize or deal with overfitting of your model. And in R, there's a package called the Ranger package that can be used for that. So don't forget that once we have nonlinear outcomes like that, nonlinear patterns like this, and keep in mind you could also transform some of those variables, especially the continuous. Keep in mind for the nonlinear aspect, we are dealing with continuous covariate. So here I decided to look at the log transforms, even the square root. It didn't make any difference. We still saw patterns. Yeah. So and once you see a pattern, then it means that nonlinearity was what occurred and linearity was violated. All right. So this is the kind of output you see to fit a survivor, a tree model in this case. And then the average would now the average can now be compared to the classical cost proportional or the Kaplan-Meier curve in that case. Yeah. So so it means that's why we call it survivor trees, because you have like different trajectories of your survivor curves, and then the average of it can be the mean curve somehow. Yeah. Okay. And then so the next thing is this is just trying to compare between the classical cost proportional regression. The KM is the Kaplan-Meier curve, the green, and then the random forest or the survivor tree. And so it means this is the average of it. So if you think about it, in this case, with using that method, we were able to achieve like higher probability of survival, and based on what you're seeing anyway. So I'm just trying to say that it's also another class of survival models you can always use and compare with the classical ones, and they have particular ways of testing the validity. Just like you fit a model and you want to now test for its accuracy. In most cases, one could use, let's say, ROC curve, estimate Gini coefficient, and so on. So these ones also, we have ways of quantifying their accuracy and so on and so forth. So the remarks is that the stratified cost proportional models are useful extension of the standard ones. Just that it's just trying to allow for those covariate with the non-proportional hazard assumptions are being controlled for. And then, but the limitation is that cannot make any inference about the stratification variables. You are just controlling for them, but you cannot make any inference about it. It's just like fitting a mixed effect model. Once you consider some class of variables as random effect in your model, you cannot make any inference about them. You are only controlling for them because you believe that they introduce some hierarchical structure to your data. And then, keep in mind that a larger limitation of stratification is if you are dealing with continuous variables. So often it's not nice if you have a continuous variable and it didn't achieve this the constant proportional hazard assumption. Sometimes one way is to recategorize or to categorize that continuous variable and see if that will solve the problem. But again, if you don't know exactly how you want to split it, it also introduces some degree of challenges. Yeah, so that is one of the limitations. And so it means that stratification is less useful. But keep in mind, is though we believe that it helps with controlling for that non-proportional instances as an assumption, but you realize that variable is completely, we can't make any inference about them. But what if you want to make inference about them? So we now talk about the multi-state Markov model, which can actually deal with all the various limitations that I've mentioned in a more robust way. But keep in mind, stratification is really, it's not very useful, especially when there's non-proportionality with respect to the treatment that you are trying to investigate into. So that's just one thing. So in summary, you can always think about stratification as when you have like aggregated results across maybe multi-center studies, so where you are not interested in the multi-center studies, but you believe that the results could change from centers to centers. In that case, you can now stratify your model with respect to that variable and so on. So it means if you have some variables of interest or variables that you believe you want to consider them as a predictor, and then you don't want to just stratify them and lose your inference ability on them, then you now have to think about what you call multi-state Markov model that extends the standard survival models. Now, if you think about it, one of the major limitations of the Kaplan-Meier and all the survival models I've mentioned, including the survival tree and all sort of things, is that you realize that the outcome variable or the primary endpoint, if it is the time to, let's say, death, I'm using that as an example, or the time to experiencing an adverse event, or the time to experiencing anything. So if that is your outcome variable, now think about it this way. So you realize that before death occurs, maybe if the individuals who started the study were infected. So it means that those models, when you talk about the censoring status, it's either you are dead or alive, isn't it? So those who are alive still within the observational period are assumed to be censored, right censored. But one thing we have to notice that if an individual is alive, the individual could be alive but still with the infection, and the individual could be alive without the infection. But the classical models I've mentioned does not take that into consideration. That is just one of those instances. Now, we are also going to look at situations where you want to study disease progression before death occurs. These methods that I've mentioned already, or that the ones that we are often used to, are not able to deal with such instances where we are trying to look at the progression or studying the progression of an infection, and then trying to still model the survival times as well. Yeah, and so it means that multi-state Markov model is a direct extension of the classical survival models, and is able to deal with time-varying covariates in the best possible way. And even when we have non-constant hazard, is able to deal with that. So this is just I'm almost wrapping up. So basically, if you look at this model, so situations where now we are trying to look at time to death, okay, and death is the absorbing event. And so in mathematics or statistics, when you say an absorbing state, it's more like a state when once an individual enters that state, they cannot leave that state. It means once you are dead, you cannot be reinfected or you cannot move outside that state. So that is what we mean by absorbing state. So it's not only death that can be seen as an absorbing state. Once you have some disease state such that once you find yourself in that state, you cannot leave that particular state. That state is called an absorbing state. So now think about, let's say, this classical kind of disease progression model where you have a set, maybe HIV stage 1, stage 2, you have different stages. And then it means an individual could either switch from stage 1 to stage 2, and at a point can switch from stage 2 back to stage 1, or could switch from stage 5 to stage 6, and so on and so forth. Even if it's possible that an individual could even, it's not possible you could switch from stage 5 to, let's say, stage 3. But even if that was possible, we could still model it. And this transition matrix will cater for that. So it means wherever we see zeros, it means that there's no possible transition in that case. So that means that if you think about it, the multi-state Markov model actually improves upon the effect sizes of the classical survival models, in that we are able to also now look at these other complex relationships, right? Or transitions that would exist in your data before death eventually occurs. Imagine if we're using a classical cost proportional model, all the disease and stages and transitions are automatically ignored. So here, if you assume that all the transitions here are basically 0, or then it means the output of the multi-state Markov model would just be the same as the classical cost proportional model. So it means that there's a package in R that can be used. We call the MSM package, and then they are vignettes on it. And so the most important thing is that it's used to investigate disease progression models, not just disease progression. I'm going to talk about a certain application, which is one of my works, and tell how I borrowed the same idea to model that. It means that, which irrespective of the study you are doing, maybe you've already done some survival analysis. It's possible you could reanalyze your data if you believe that there are possible transitions that could occur, or possible transition between some dependent states that could occur before your final, or before the maybe death or any absorbing state of interest occurs. Then we have multi-state could be useful for that. And most of the times, if you have chronic diseases, I mean, it's more often a natural interpretation of a stage progression, which you could always use that. Okay, so I think we are literally done. So here I'm just touching a bit on how I use this multi-state Markov model, though this is predominantly for an epidemiological study, but here I decided to use it in a pathological study. Of course, once you get the slides, you can click on this to see how do you call it, to see to read the paper itself, and also look at other proposed methods that we developed. But here, this is something that I wanted us to realize. So this is a study where we literally infect a fish with some number of parasites, and specifically they mostly start under experimental conditions. They start with 2 parasites, and then they decide to record a number of parasites over time. But at the same time, at any point in time, is the fish dead or alive? If alive, did the fish lose the infection or not? They collect all these data. So this is the data that I have. And then the goal was to investigate 3 important research questions. We're trying to investigate questions about the intra-population dynamics of these parasites, host parasite system. And we're also interested in trying to investigate into their survival, host or parasite survival, and quantifying parasite violence. You realize that most of the times, in the when just like the Cox proportional case, we are just looking at the time to death. So there's only one. It's more like a one-dimensional transition. But situations where we have multi-dimensional transition. So, for instance, it means that situations where we have multi-dimensional transition, or violence does not only depends on mortality. Most of the times we think that a parasite is more violent depending on the kind of causalities it can inflict. Generally, it's even 6-dimensional, but predominantly ability for individuals to recover easily from an infection can even tell that infection is not really that violent. So it means host recovery and host survival. In this case, we decided to model these 2 metrics to quantify violence. And at the end of the day, it's and that is the beauty about the multi-state model. It was able to also solve that problem for us in this case. But here, I just want us to focus on this. This is the transition rate, or let's say the hazard rate. You can clearly see that it was changing over time. So if we're using or between any observed time interval, so it means if we're using like the classical cost proportional model, clearly we're going to get a very poor fit. Okay, and even in the multi-state, we have a version of the classical cost proportional model. That is if we assume time homogeneous case. So it means we have time homogeneous multi-state Markov model, which assumes that the transition rates, or let's say the hazard rates, are fairly constant over time. But as you can clearly see, it's not the case. It's changing rapidly over time. And that is why the time inhomogeneous case is often more robust. And it means that if you fit a homogeneous multi-state Markov model and the model is not is underfitted or is not well fit, then it means the possible solution is considering a time inhomogeneous case. And that is what this paper tried to do. And then, but in the package, the way they estimate, there are other relevant metrics you can estimate from the multi-state Markov model that the classical survivor models are not able to estimate. For instance, you're able to estimate the time an individual could remain in any of these states. You could, if that's the mean surgeon times. You could even estimate like the probability of maybe. So, for instance, if you look at this here, we are looking at rate of transition by an infected fish, right? That is from stage 1. At stage 1, they were infected but alive. But at stage 2, they were alive but they lost their infection. At stage 3, they died. So, so it means that with the help of the multi-state Markov model, you could actually model your data in a multi-dimensional fashion whilst capturing all possible transitions that could occur. So this is a goodness of fit, and that's just telling how after originally we used the time homogeneous case, the model was poorly fit, but after introducing the inhomogeneous case, because clearly the transition rate was not constant over time, it was basically changing, and that you could see if you compare the prediction from the model with that from the observed data, we had a very good fit here. So, and then some predictions and so on. And of course, you could now predict host mortality conditioned on your significant covariate. You could, and keep in mind, you could do the prediction across different transitions. So in terms of the multi-state Markov model, another thing that it does is that you realize that with the classical cost proportional model, of course, you could do variables, variable selection. Maybe you have some set of predictors. You're not too sure whether you should include all those predictors in the model. And then you want to probably also enter the model in a stepwise fashion or in a hierarchical fashion. Of course, you could do all those things. But the beauty about the multi-state model is that suppose you have only 2 possible transitions, because in this particular study, there were only 2 possible transitions. So it means that an infected host or an infected fish could either lose its infection and still remain alive, or could die. Okay, so there were just 2 possible transitions. But for each transition, you can do variable selections, because it's not all the predictors that could predict that transition. So it means with the help of the multi-state model, you are able to even identify some subset of your predictors that can predict transitions from a certain state to another state, and also look at other set of predictors that predict other transitions. So that's the beauty. So it really is an extension of the standard survivor model. So this really brings us to the end of the class. So the experimental, the introductory session 2 was basically trying to touch a bit on some of the more customized methods that we often use in most studies, especially in clinical trials, or we often use in other studies. And then, so I wanted us to create our awareness about the fact that although generalized linear models are useful, especially if you're interested in just one-dimensional association, but it's not always the case that it would really tell us all the story we need to know. So that brings us to why we need to now think about structural equation modeling, especially when we want to now identify potential moderators and mediators, meaning that some other variables that could even predict the association between some predictors on the dependent variable, and also even model complex multiple dependent variable at the same time, and even explore the relationship between the dependent variables. Of course, multivariate regression does that. That is after looking at how some set of predictors predict multiple dependent variable. It also investigates the joint relationship between the outcome variables. But again, with that, it's still looking at a one-dimensional relationship. So it's just a one-dimensional association of your predictors on the multiple outcomes. But structural equation model does a lot than just that, and so on and so forth. And we said that to do that, always start with at least a hierarchical regression, couple that with a moderation mitigation analysis, just to see if there are potential moderators and mitigators. Once you're able to establish that, you can now come up with a structure, and that structure is what you are basically going to confirm, and that is what we mean by doing a confirmatory factor analysis. And then each path in the confirmatory factor analysis is basically a regression. So that's why structural equation model combines path analysis with confirmatory factor analysis. And then we touched a bit on survival models, and we said that for survival analysis, you have the unstratified and the stratified. And we said for the unstratified, the Kaplan-Meier is just one of those methods. And then the cost proportional, the classical cost proportional regression is an unstratified method. If you Google, you are likely to think that the cost proportional regression is stratified. It is not stratified until you stratify those predictors that did not achieve the constant hazard proportional assumption. So that is, and then remember, if you stratify your Cox proportional regression with respect to those specific structure that resulted in the non-constant proportional assumption, remember that we cannot make any inference about them. We are only controlling for them. And so often it should be some variables we are not really interested in, but they probably maybe introduces some structure to our model. Or it's possible you have some continuous outcome, that a continuous predictor that resulted in a non-constant proportional assumption, but it's a predictor you can do without, meaning that you can actually categorize that and check if, upon considering that as a structure in the model or as a structure in the model, would it improve or help achieve the assumptions and so on. And don't forget that cost proportional hazard regression is a semi-parametric method, which assumes and expects you to test for parametric assumptions, and most importantly, the constant hazard assumption, and don't forget the linearity assumption. And then when you have a time varying covariate in your data, it is very likely that it is very likely that both the stratified and unstratified Cox model might not be able to deal with that. So in that case, it brings us to another class of model called the alien additive regression, which I've mentioned. And then we've now talked about how the multi-state Markov model extends the classical survival models to now model, or to still look at the time to experiencing a certain outcome, a certain event of interest, but also exploring all possible transitions that could occur before the absorbing event eventually occurs. And so that is basically what we did today. And then you get access to the slides. And don't forget, this meeting is recorded. Future times we talk about functional data analysis, which I think I just said that it's very new. It's a recently developing methodology, though it has been in existence for ages, but most researchers are not aware of. As a matter of fact, most statisticians are not even aware of this. And so functional data analysis, we realize that all the analysis we're doing, or the analysis you've been exposed to, are always modeling your data in real space. But what functional data analysis does is that it converts your data from real space to a certain space called the Hilbert space. At the Hilbert space, it means you transform your data basically to a set of curves. And these curves are in a functional form where you can integrate to or differentiate to get rate of change, and so on and so forth. I use that to discover a very novel. I did a competition where we're supposed to use machine learning techniques and advanced techniques to investigate into osteoarthritis infection, and then and through that we're able to use the functional data analysis in a way to have an important discovery. I mean, I can just maybe spend 2 minutes to explain that. So what happened was that, the surgeons, or let's say the orthopedic surgeons, they realized that after treating patients, they have a particular quantity that they use to classify whether they are doing well or not. And so they realized that once they treat a certain patient, there are instances where there's a certain period of remission where the patient does not experience any pain. and then at a certain point in time, then the pain starts occurring. But they didn't know for how long it takes for the remission period to occur. So with the help of the functional data analysis, we now took a very large data in the US and then looking at that point. So meaning that to do functional data analysis, we expect your data to be longitudinal. And then situations where you have a longitudinal data, you want to explore patterns. So you can actually use it to explore patterns. And all the conventional statistical methods, we have its functional form. So it means we could have a functional ANOVA, we could have a functional component analysis. So it's a whole class of a whole class of statistical method on its own, which extends the classical ones we know. But the only take-home message is that it models data as curves, not as real space, and so on. Yeah. So again, I would put the video on the YouTube channel, so you could just watch it and learn at your own pace. And so thank you very much. And if you don't have any question, then I guess we could end today.